spell backwards is wrong.
Did you know dad spelled backwards? That's bad.
Dad.
No, it would be bad.
All right, go to, yesterday you guys did exercise 12.
You wrote it backwards, the D, but like B.
Page 28 where you need to be. Page 28. Okay, what page is it supposed to be on?
28.
What page is it supposed to be on?
28.
Okay, so those of you that aren't on 28, I hope you got that. Get there, please, if you're not. Okay, again, okay, if you guys look in Canvas when you go to the study hall, okay, these are what to do. Okay, look at the assignments. Week 3, yesterday, you should have the tautology and contradiction assignment done, which was exercise 11, which we did half of it in class. Okay, that's what should have been done like over the weekend. You should have turned it in yesterday. Okay, then today was due when you guys get to study hall. Okay, is exercise 12. It should be done at the beginning. It should be done right now. Like, that's what we did yesterday. We did the first question of question 12 yesterday, of exercise 12, and then you guys are supposed to do the second question and finish the truth table, right? Okay, so if you didn't do that, then it's the difference between 0, 5, and 10 points for you. Okay, it's get your stuff done, you get points. If you just get it done. Okay, then our TAs, they go and grade it for you. They're going to tell you if you screwed up. Okay, and I do have the assignment with you, so it shouldn't be too much. Okay, today, when you go home tonight, the questions you should start working on. Okay, our exercises 13 is what you should get done today. This assignment, Theorems of Logic and Arguments assignment, it includes questions 13, or exercises 13 and 14. What you need to do tonight, let's be very clear, is question, or exercise 13. Which exercise? 13. So tomorrow night, you're going to do 14. So this assignment is 2 days long. Make sense? Questions on what's due this week? Yes?
Will we get any more homework on Wednesday, tomorrow? That will be due on Thursday? Or will we just...
Again, tonight you do question 13. Tomorrow you do 14.
Okay.
That's it.
Okay, and then it's due on Thursday.
Yes, and you have a quiz Thursday that's all of this stuff.
Cool.
Okay? So the quiz on Thursday, okay, if you were to look in Canvas once again, look at this. It says students will take quiz 2 in class, and the quiz will cover exercises 11 through 14. So to study for the quiz on Thursday, you need to know how to do exercises 11 through 14. And you're expected to have those exercises done before the quiz because they've been assignments, right? Okay? And it is open book like the last quiz. Questions? Alright. Hopefully that is helpful. We're on page 28. We talk about theorems of logic. So, what's a theorem? We've talked a little bit about theorems. What's a theorem? Who can explain? Trent, right?
Yeah.
Okay.
A statement of mathematical truth that can be proven.
Statement of mathematical truth that can be proven. Good. Any other ideas or explanations of a theorem? That's good. Okay. So the algebra of statements. So theorem 1. Okay, the algebra of statements. So we're going to look at these statements. Okay, the first one is closure. The disjunction of P and Q. So we got to look at our let, right? This is what we know. We know P, Q, and R are any three statements. Okay, we just know there's some statements. We don't know what the exact statements are. We just know P is a statement. We know Q is a statement, and R is a statement. Again, we don't know what this statement actually is. We just know they're labeled P, Q, R. Okay, so if that's true, if we know this, then we can say the disjunction of P and Q, or P or Q, is a statement and the conjunction is a statement. So there should be a T right here. You can add that little T right there. Okay. So it's really stating the obvious here. Okay, on this. When we have a closure, we're just saying P or Q is a statement, and P and Q is a statement. That's going to give us closure. Okay. Commutative properties. If P, Q, and R are any three statements, here's some commutative properties. P or Q is logically equivalent to Q or P. And P and Q is logically equivalent to Q and P. Okay, for any statements P and Q. So, some we already knew. Some of this, we've covered this already, right? We talked about commutative property with our conjunctions and disjunctions. They're commutative, okay, they're logically equivalent, meaning they have the what? If they're logically equivalent, what do these two statements have?
Same truth value.
Huh?
Same truth value.
Same truth value.
Same
Table, sorry. Questions on that? Okay. So nothing new yet, right? Associative property. Okay, you guys have seen the words commutative and associative, right? Okay, when we talk about commutative, that's 3 plus 4 equals 4 plus 3, right? Associative is when we move what? The parentheses. So it's the same thing here. If we have P or Q or R, we can move the parentheses from here to here. That's logically equivalent. Okay, these are logically equivalent statements, these disjunctions. The conjunction is also true. We have associative property for our conjunctions. Okay? Associative property, move parentheses. Identity properties. If C is a contradiction, so we're throwing in a new statement. Okay? C hasn't, we've talked about P, Q, and R so far as our let part, right? So let's just say if we have another statement C, if C is a contradiction and T is a tautology, okay, so this is our condition, if, okay, this is a conditional thing, right? So if this is true, then we can say P or C is logically equivalent to P, and P and T is logically equivalent to P. So again, these are just, all of these statements that we're going over right now are just going to be tools for us to use. Okay? They're going to be tools for us to use. So it's like our math tool bag. Okay? So if we had a toolbox full of math stuff, these would be in. Okay? Inverse elements. Okay? Again, if I have P or not P, right? The disjunction of P or not P. Yes? That's logically equivalent to T. And that's given that T is a tautology. Okay? P and not P is logically equivalent to C, given that C is a contradiction. Questions on any of these statements so far? Yes?
So when it says P and not P is logically equivalent to C, that just means it is, right? Like P and not P are.
Okay, let's do this. So let's say P and not P. Let's assume P is true and not P is false. Okay? Let's just assume that. Because that's all the not does, right? Is it changes the truth value. We're saying that's logically equivalent to, in this case, where are we at? C. And C was a contradiction. What's a contradiction? What's a contradiction?
All of that column is false.
Huh?
All of that column are false.
All of that column are false.
So all the column for that that statement for that
So when we have a conjunction, yes? Yeah? So that's and. So P and, not P. When is a conjunction true? When's conjunction true?
when all is true.
When all is true. When's a disjunction true?
When one is true.
When one of them is true, right? So in this case, we have a true and a false, yes? And you guys are saying the contradiction is false. So is this statement false? It's logically equivalent to this one too, right? The truth tables are the same. False, false. Okay. You see it? The answer, who's had the question? You? You good? Good questions. You like questions? Those are fun. Where's the mouse? Okay. Distributive properties. Okay, we talked about distributive properties already. Right? Or was that my other class? I get confused between this class now and grade structure sometimes.
Yeah, we did not.
Okay. So distributive property, much like if we had numbers, okay, if we're going to distribute a number, okay, it's kind of got the same idea here, but the signs flip. So if I have a normal distributive property like 3 times x plus 5, I distribute the 3, right? Distributive property. Well, it's true here with our statements. If I have P, a disjunction of P with Q and R, I can say, well, I'm going to distribute here, so I get P or Q. Okay, see that? See how the or goes with it, P or Q, and then P or R. But there's this conjunction that has to stay between. So, if I move this down a little bit, I can show you how it kind of connects the ideas. Okay, so look at this, P or Q. That's this right here. You see it? So if I was to distribute the P and the or, basically, you go with the Q. Then I've got P or R right here. And then this conjunction has to go right here. So that's where the distributive idea comes in. Did you guys see the distributive property in that? Who does not? That's my question. Where do we need help on seeing it? Where do we need help on seeing the distributive property? Don't know? Okay, heads down. Okay, who feels like they're understanding so far today? So far today you're understanding. Raise your hand. Raise your hand if you're just kind of understanding today. Okay, raise your hand if you're lost. Okay, hands down, heads up. Okay, I need to know where we need help. If we're lost or kind of understanding, we need some clarification, right? So I need you to point out where you need help so we can talk about it some more. So I can ask some more questions. So I can ask questions, we can get stuff pulled out of your grades a little bit, okay? But I just need to know where we need to help. Yes, mate.
So, I'm getting most of this, but what does the market have to do?
We're not there yet.
Okay.
So from here up, do we understand?
Yes.
Okay, good. Okay, so De Morgan's properties. Okay, these are just other rules. Okay, some other rules we have, some other facts we have. If we have the negation, okay, we've talked about our De Morgan's laws already, right? Remember you guys had to use those back on our quiz and on an assignment? Okay, we have the negation of the disjunction of P or Q is logically equivalent to the negation of P and the negation of Q, and the negation of the conjunction of P and Q is logically equivalent to the negation of P or the negation of Q. And this is nothing new here, just another property. This whole page is, like I said, a toolbox. So you need to like star it, like we did example 12. You guys had example 12 back like a couple, like last week sometime, where I said, hey look, there's all these rules, you need to know where they're at. Okay? So again, lots of rules, just know where these are at. So star this page, or fold it down or something. Okay? These are just a bunch of rules that we need to know. So, I don't even know if I can say something. Idempotent properties. Okay? P or P is logically equivalent to P.
Yeah.
Makes sense, right? P and P is logically equivalent to P. P or T, assuming that T was a tautology, right? Is logically equivalent to T. P and C is logically equivalent to C, where C is a contradiction. Okay? A corollary. So this is all theorem 1. Okay, these are algebra of statements. Okay, these are just, again, rules. Think of them as rules that can be proven. Okay? Next we have a corollary. Okay, a corollary is kind of like a buddy to a theorem. It's like, since theorem 1 is true, like theorem 1 works, and we have the theorem, everything can be proven. These are other things that we can assume because of theorem 1, our corollaries. So that's all the word corollary means, is like, hey look, these are some added things that we know because of theorem 1. Okay? We know theorem 2 is called the reflexive property. For any statement P, P implies P. Okay? Then we also know anti-symmetric property. If P implies Q, and Q implies P, then P is logically equivalent to Q. Okay? Transitive property. If P implies Q and Q implies R, then P implies R. Because look, P has to imply Q and Q implies R. They kind of connect right here, so therefore P has to imply R. And that's called the transitive property. If P implies Q and Q implies R, then we can assume that P implies R. Okay, rule of modus ponens. Okay, we've looked at this rule. Okay, we have the conditional statement of P and Q as a conjunction with P implies Q. Okay, again, these are just rules. Rule of modus tollens. Okay, if P implies Q as a conjunction with not Q, that implies not P. These are all things we've looked at in truth tables. Okay, we've looked at these rules in truth tables. Okay, yesterday you guys worked with implications. To show that an implication is indeed an implication, we had to show that it's what? What do we have to show that an implication works? What do we have to show yesterday?
Like it with the
Conditional.
Yeah, with the conditional statement and tautology.
Yeah, we have to show that its conditional statement is a tautology, right? All we do is we change this arrow to the skinny arrow, and we show, hey, yeah, it's a tautology, therefore it's an implication here. The implication is true. Rule of hypothetical. If P implies Q as a conjunction with Q implies R, implies P, as a conditional statement with Q and R, that implies P, which is a conditional statement with R. Okay? A lot of stuff there. Okay? Another rule. Okay, just another rule. Okay, theorem 8. P and Q implies P. The conjunction of P and Q implies P. P implies P or Q. So P implies the disjunction of P or Q. Yes?
What is a theorem?
A theorem is a rule that can be proven mathematically. We'll just leave it at that. So these are just different rules. Think of the theorem, oh, that's a rule, that's a rule, that's a rule. It means it always works, no matter what. Okay? What's up? What do we need?
I need to go to the restroom.
You just raise your hand, go ahead. Okay, who's going to read for us? Definition 14. Go, Trent.
An argument is an assertion that the conjunction of two or more statements called the premises implies another statement. This implied statement is called a conclusion. The argument will say that way that the conclusion is derived from the premises.
That's a mouthful, right?
Yeah.
Okay, let's break it down. An argument is the assertion. What's an assertion? An argument is the assertion. If you're going to assert something, what are you doing? Yes.
Putting physical effort into it.
Huh?
Putting physical effort into it.
Okay. Getting there. Not quite. If we're asserting something, we're approving of or giving an effort into it, maybe is where you're going at. Yes. So we're giving it that assertion, that approval. Okay? That the conjunction of two or more statements. So we have the conjunction, let's just say the conjunction of two statements. Was that two statements? Is that a conjunction of two statements?
Yep.
Okay. Called the premises implies another statement. So they're saying an argument says, look, if I take a conjunction of two statements or more, two or more statements, that will imply, okay, this is the premises. You guys should write this down above the, write it down above the definition here. Premises, okay, it implies another statement, let's say, are. Okay? So, two or more statements. Now, this is 1, 2. Okay, you can have more statements over here. It implies some other statement. Okay, that's our argument. This implied statement is called the conclusion. So, premises, and this right here is called the conclusion. Again, write this down. So some of you don't have pencils going, I'm worried. The argument will say that the conclusion is derived from the premises. So now we've got our pieces. We've got our one or two arguments, so this is just going to be, our two statements. You can have two or more, right? Yes? Okay, two or more statements, conjunction of two or more statements, implies another statement, which is called the conclusion. So this is an argument. Questions on what an argument is? Okay. Definition 15. Need another reader. Go.
An argument is valid if and only if the conjunction of the premises implies the conclusion. The conclusion of the premises is also called the hypothesis. We said that an argument is valid if and only if hypothesis, then conclusion is a tautology. If it can be shown that there is at least one case where the hypothesis, or if the hypothesis, then the conclusion is false, then the argument is not valid.
Okay, kind of a review from yesterday, right? So if we, again, break it down, an argument is valid if and only if the conjunction of the premises implies the conclusion. So, to show that this implies the conclusion, we have to show that the conditional statement is what?
True.
Is a tautology. So, P and Q have to be, this has to be a tautology, right? That has to happen for the argument to be valid. That's all that definition is saying. Okay? Also, we call the premises what else? What's another name for the premises? Yes?
Is it a conjunction? Or antecedent?
Close. Yes. Hypothesis. Okay, that's what they said in the definition. Okay? We have known as the hypothesis. Okay? Premises is also called the hypothesis. Okay? Lots of definition here. Do we understand the definition now? The question, heads down. Heads down. Okay, definition 14 and 15, the ones we just read, we just broke it down. How many of you wrote it down like you're supposed to, the stuff I wrote on the board? How many wrote down the stuff on the board? Okay, hands down, heads down, keep your heads down. Okay, how many of you understand the definitions that we just went over? Alright, you kind of understand the definitions. Maybe you're lost. Hands down, heads up. Okay. So, questions? Yes, Maddie.
How do you determine if an implies is true or false?
So how do you determine if this is really an implication, really if it qualifies an implication? Is that what you're asking?
No, if it's true or false.
True or false?
How do you determine the true value of what you made?
Yes.
It's an argument, so it's a hypothesis and a conclusion, is what we're getting at right now. But yes, you're going to use the truth table for the conditional statement. I don't know that we make a truth table for the actual implication. Because we're saying that it works, it is an implication. We're implying that if we have this, then this is happening. Like, we're implying. Okay? Let me think about your question some more and see if I can come up with a better answer for you, okay?
Okay.
But right now, the way we're going to make a truth table for the conditional statement of the implication, right? Because all we do is change that arrow sign. And then we're looking to see, make sure that this is a tautology, that its truth table is all true. So, kind of the same thing, but not. Good question. I'll have to think about that more. But that's what I got for you for right now. Okay, example 17. So really, this is kind of like the same stuff that we talked about yesterday. Okay, if we look at example 17 here, the following argument is valid. The rule of modus ponens, okay? We have the conditional statement the conditional statement P and Q as a conjunction with P, that implies Q. So you make the truth table for it, and we're just showing, hey, look, if we make the truth table for this implication or this argument, okay, we make the truth table for the argument, we show that, hey, we have a tautology right here, right? So that means our implication is valid. So maybe that we don't, and I need to get back to your question, we're checking to make sure that our argument is valid, which is our implication, okay? So we just said, yep, our argument is valid. This is an argument. It's valid.
Yes, but I'm like talking about implication. I never asked you that question.
That's an implication, right?
Yeah, but let me give you an example. So for example, if I had P and R implies Q, and P and R is true, would the whole thing be true, or would it be false?
It depends what truth value Q has.
If Q is false, then will the whole statement be false?
So you would have to say, look, if you're saying this, P and Q, or P and R, right?
Yeah.
Implies Q. Well, if you take this and you make a conditional statement for it, then you have to check to see if your implication is valid. So you have to check the conditional statement. The implication is checked by the conditional statement.
Okay.
So-
what you're saying is that if the bottom of the arrow is true, then it implies also true.
If this is a tautology,
That is okay.
then this is an implication. This is a valid argument.
Okay.
Make sense?
Yes.
Okay, that's what definition 14 and 15 are getting at. So hopefully that helps a little bit. So really, all you guys got to be able to do is, hey, we have a theorem, fill in the truth table. Okay? You have a conditional statement here to show that your implication is true. If it's tautology, then it's a valid implication. So this is the big part right here that we're going to be looking for, is this sentence. I like this sentence. Okay? What's our three dots mean?
That is a good question.
Go find it. Someone go find it. Three dots. Look at your symbols. When you have it, raise your hand.
Find it. Found more three dots.
Is that not in your guys' book? Let me look real quick. I thought we covered it in here.
This is broken. I see it.
Maybe that was my other thought. Maybe that was algebraic structure. What?
Look like in the future.
I sent you guys on a goose chase.
I'm pretty
It's like duck goose. When
Focus though.
yeah, that was my other class. Sorry, guys. Go back to page 20. I think this is 29 or 30. Okay, go back to page 29. Sorry. I like that sentence, though, that I asked you to highlight, please, while you're waiting. Sorry about that. I sent you guys on a goose chase. That was my other class. So we're going to assign the three dots a name. Three dots mean therefore. Okay, or sometimes they use it to start a conclusion here. Okay. I'll explain just a second. Okay, if we're showing a proof, we're making a mathematical statement, okay, this is signifying, hey, we're making a statement. Okay, so we have our information here. What you guys have to be able to do is be able to write me a logical sentence on why the statement is valid. Okay, here's the sentence you have to be able to write. Since our conditional statement of the conditions P and Q, or P of P and Q, and the conjunction with P with Q is a tautology. So if this statement, since this statement is a tautology, it can be stated that our conjunction of P with our conditional statement of P and Q implies Q. Thus, the given statement argument is valid. Okay? So, what you guys are going to have to be able to do is write this sentence with different values right here, a different value right here, depending on what statement or argument you're trying to show is valid. So we're just saying, since blank is a tautology, it can be stated that blank is a valid, it can be stated that this is an implication. Therefore, thus, the given argument is valid. So you have to be able to tell me, basically in a sentence, that this is why the argument is valid. The argument is valid because it is a tautology. Okay, it's just formal. This is a formal way to answer our questions. Okay, the formal way to answer our questions. James. Who got out? Someone else went out. They get back. Abby just went, and then okay, well, Billy's back. Okay,
Why does everybody have to move back?
I do not know.
because you're just drinking too much water. Okay, questions on how to answer this question? Okay, look at example 18. We want to show that this argument is valid or invalid. Okay? So this argument is not valid. If we look at it, okay, we have the conditional statement P and Q as a conjunction with Q implies P. So this statement is not valid. The reason it's not valid is why? Why is this statement not valid? Yes?
We have a false in the third row.
We have a false. Where?
In the third row. Third row of the truth table.
Oh, right. Oh, row. Okay, sorry. Look at yes. False right here. Yes?
Yes.
That's what we're looking at? Okay. So in our truth table here, the conditional statement of our argument, okay, shows that one there's a false. So it's not a tautology. If it's not a tautology, it's not a valid argument. Okay, so the way you would state something that's not valid, okay, notice guys, on your question you guys are answering today, on your homework, you need to start it as prove. Okay, you're going to write the word prove. You're going to make your table. Okay, make your table. And then you're going to say, since our conjunction, our conditional statement of P and Q as a conjunction with Q if this statement, our conjunction of if P then Q as a, I'm saying it wrong, the conditional statement of if P then Q as a conjunction with Q, then P is not a tautology, then the argument is not valid. Okay? That's or invalid. And this little box, that's about the box.
What?
That's about the box here. That's the end of proof. It's like putting a period at the end of a math sentence.
So do we have to put that?
Yes, you need this. I want to see this on your homework and on your quiz. So on your quiz, what you're going to get, you're going to have to fill in a truth table. You're going to have to say, well, this is a valid or invalid argument, and it is a tautology or not a tautology. Okay, you got to keep these things on your guys' assignment and quiz. Questions? Okay, so here's a little sentence here. Who's going to read for us this first paragraph to understand? Tatum? Will you read it for us? Will you read it for us?
Not straight.
But will you? I know you don't want to, will you?
No.
Okay. Maggie?
What am I reading?
The highlighted stuff. To understand.
To understand the above example, consider the following. We could say, if the animal is a beagle, then it's a dog. However, the compound statement, if the animal is a beagle, then it is a dog, and the animal is a dog, does not imply that the animal is a beagle.
Okay.
Dog.
So, here's the fun part. Where's my marker? So if we look at this, if we take our statement, okay, consider if the animal is a beagle, then it is a dog. Okay, that would be our if P then Q. So P would be if the animal is a beagle, Q would be then it is a dog. Okay, it is a dog is our Q. Yes. Okay. If we take that as a compound statement, so here's our compound statement, we're going to say, well, if P then Q. We have the if P then Q. If we put that as a conjunction with Q, if the animal is a beagle, then it is a dog. And, that's this part, and the animal is a dog. That does not imply the animal is a beagle.
You just read it exactly what I read.
Yes. Because we got to get in our head several times. So this is an example of why this argument is not valid. So this is an example to help you understand why this is not valid. You need to read through it a few times. So this is how you would write it. It doesn't make sense, right? Okay? So note. Big note.
I want to read it.
You just read it. Someone hasn't read it yet. Okay, go for it.
If the hypothesis implies a conclusion, then the argument is valid. However, that does not mean that the conclusion is true. For instance, example 17 presented an argument that was valid. However, statement Q, the conclusion of the argument, could have a truth value or false. Validity only tests the correctness of the argument, not the truth value of the conclusion.
Okay, going back to your question earlier, Maggie. Look at example 17 here. Okay, they're saying if you look here at example 17, okay, we have. Let me see if I can. Sorry, I got to scroll down just a little bit more. In example 17, now I'm going to leave example 17 up here. The note. Remind me your name. Kara. Okay, sorry. So, if we look at this argument, here on example 17, the statement Q, the conclusion argument, could have a truth value of false. Look at Q. Q is false here, and Q is false here. Right? So, false and false. In our implication, Q, we're saying it implies Q, you can see it right here. There's an implication of Q right here. Sorry, I didn't scroll it down quite far enough. That means Q would be false. So coming back to Maggie's question earlier, we're not testing where it's true or false. We're trying to see validity. Okay? So it's the correctness of the argument rather than the truth value of the conclusion. And we don't care about the truth value of the conclusion so much as the correctness of the argument. If the argument is correct, then its conditional statement is what?
Correct.
It's a tautology. Okay, we're looking at validity of arguments. To see that an argument is valid, we look at the conditional statement and say, yep, that's a tautology, it's a valid argument. Okay? Okay, exercise 13, you have a table there. That's your assignment, ready to go. That's all you gotta do for the rest of the day. Yeah. What values are missing? Hey, look, you guys. The question is, what do we put in the empty boxes? Well, I know that we're going to need not R and not P eventually, right? So that's going to have to go somewhere. We're going to need, so we got if P then Q, we got if Q then R. If P then Q has to go here. We have to know that truth value. We have to know if Q then R's truth value. And we have to know not R and not P. That help?
Yes.
Fill in the truth table. Yeah. I don't know that I would say distributive. It's just an argument. We're trying to see if it's valid. You know? It's not a specific property right now. If you've seen something like that, then it might be helpful to look at something like that, yes. Hey, remember, yesterday we had a 3-statement situation, right? Started out the same way we did the one yesterday. True, 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 right? Okay, and so on. Fill it out in the same way. These first 3 columns should be the same as the one yesterday. Okay? Don't make them different. Don't do any magic. Just do the same exact ones we did yesterday. Right here. The first 3 columns. No magic. Yeah, I'm gonna give you guys a couple minutes to work on some of that. You guys can ask some more questions as I come around. You guys, really, this is all we gotta do today is get this one done. Just check. As long as you have all options, you're okay. So you just take false over each time. See false here, false here. As long as you have all combinations, it's fine. I try to do the same one each time so that it's not, it's easy to memorize. And so your schools, I checked these ones. Yeah, it's good. Q is, I mean, it's gonna be true or false. Yeah, whatever, you just, that's okay. Good job. Yeah, no, smart job. Yes. So we have a true, true, true. So we have it P then Q. So if P is true and Q is true, so we use for this cell we use what's happening right here. For this cell we use what's happening right here. For this cell we use what's happening here. Yeah, true, true, true is good and true. So Q, yeah, that is true. Yep. I would honestly work down this way. That's just my personal preference. So I'd say P's and Q's, so it's true, true, true. True, true, true. True, false, is gonna be false. True, false is gonna be false. False, true is gonna be true. True, true is gonna be true. False, false is gonna be true. Right? Because the only time our conditional statement's false is if it's true, false. So I would just do that straight down this. Then you have another condition. Yep. You have another conditional statement right here. Okay. No, that's gonna be false, false, that's true. Yeah. So look, if I have false and a false, it's true. Okay? So the only time you're gonna have false is true, false with P and Q. So you're ignoring the column R while you're doing this fall. For a conditional statement. Yep. So that's gonna be back in our previous notes. So you have the conditional statements, conjunctions, and disjunctions. Those are like the key to everything. So that's all you have here is conditional, conditional. These two statements make a conjunction. So you're gonna use these two cells to answer this question as a conjunction. Okay. And then you're gonna use, you got not P, not R, not P, then you're gonna use R, not P to answer this. Does that make sense? Okay. Do you think you got it? Okay, bud, I want you to fill in these two columns and call me back over and I'll check these two columns. Okay? You got your truth tables done?
Yes.
Number 13, it's all done.